Problem number 2. The last one I realized was a little bit staticky after listening to it. I apologize for that. I put the microphone at a different spot so that it wasn't quite so hard to listen to, but I was not about to go and record that again. So you guys suffer through one crappy recording. This is problem number 2. We're asked to calculate the equilibrant of these forces. The equilibrant, again, is the force that's going to balance out this system. To, again, visually inspect these vectors, it sort of seems like the net force will be up and to the right. Maybe down and to the right a little bit, I'm not really sure. But it's clearly not going to be in equilibrium. So what we have to do is figure out, well, what is right now the net force in the x direction? And what's the net force in the y direction? And if we do that, then we can say, okay, well, the equilibrant force has to have the opposite of those two resultant forces in order to balance things out. So let's go ahead and draw the component forces based on the angles given. So we have here F1y and F1x. Here we have F2x and F2y. And here we have F3y F3x. And so we can calculate each of these. F1x, F1y, F2x, F2y, F3x, F3y. Alright. Well, this is nothing new. This is exactly the same thing as what we've done in the past unit with vectors. So, for F1x, F1x happens to be opposite the angle 25. So we would have 50 times the sine of 25. And F1y happens to be adjacent to the 25 degrees. So we'd have 50 times the cosine of 25. Go ahead and pause this and calculate all of these forces, compare with each other, and make sure that everybody is understanding how to get the answers for these components. Okay, here's what I got for my answers. Notice that F1x and F3y are negative, because F1x is pointing to the left, F3y is pointing down. Well, we know then that the sum of all the forces in the x direction must be equal to 0, and the sum of all the forces in the y direction must be equal to 0. That means that F1x, negative 21.1, plus F2x, 59.1, plus F3x, 77.9, plus F equilibrium, or equilibrant, x, must be equal to 0. In the same respect, the sum of all the forces in the y direction must be equal to 0. So therefore, 45.3, excuse me, 45.3 newtons. Okay, Mr. Kennyhood was interrupting me there, so I had to pause it. Now I'm back, which you probably didn't even notice, because it was just a glitch in the video. Alright, where were we at? 45.3 newtons plus F2x, or sorry, F2y, 10.4 newtons, plus the negative 45 newtons plus F-E-Q-Y. Now, you can solve that then for F-E-Q, the equilibrant in the x direction and the equilibrant in the y direction. Go ahead and do that. Okay, hopefully you got the same thing as me. Hopefully I didn't make a mistake. But I calculated that the equilibrant in the x direction must be equal to negative 115.9 newtons. That would make the x dimension of this equilibrant negative 115.9 newtons. And the y was a negative 10.7. Oops, I can't hardly read that, I apologize. So the equilibrant then is actually in that direction. And now you can calculate that equilibrant with your standard trigonometry. And go ahead and do that now and compare your answers to see what we get. Remember, we need both a magnitude and a direction. Okay, I went ahead and calculated this, and I used inverse tangent to calculate that this angle was 5.3 degrees, and I just said south of west. I'm not really sure that this gave us compass headings, but just for easiness sake, I said south of west. And used Pythagorean's theorem to calculate the resultant force, or actually the equilibrant force, excuse me, of 116.4 newtons at 5.3 degrees south of